Today I'll be going over 5.7, which is apply the fundamental theorem of algebra. So the theorem is, if f of x is a polynomial of degree n where n is greater than 0, then the equation f of x equals 0 has at least one solution in the set of complex numbers. And the corollary is, if f of x is a polynomial of degree n where n is greater than 0, then the equation f of x equals 0 has exactly n solutions provided each solution repeated counts as the number of times it is repeated. So basically all that means is whatever your highest degree is, that's the number of zeros or solutions that you can have in your equation. Okay, so for the first two examples, we want to identify the number of solutions or zeros. So again, all we're looking at is the highest degree. So in the first problem, that's 4. So that means there's going to be 4 zeros. And I wrote zeros for this because it doesn't say it's equal to 0. And then for number 2, our highest degree is 12. So that means we have 12. And I'm going to write solutions for this one because it says equals 0 in the problem. So yeah, that's it. You just look at the highest degree and that's the number of solutions or zeros that you should have in the problem. But the repeating part, the part that says provided each solution repeated counts as the number of times it is repeated. So x plus 1 squared would equal x squared plus 2x plus 1. Whoa, sorry, I don't know what happened. Okay, there we go. So this should have 2 zeros or 2 solutions, but it's just repeated because it's x plus 1 squared. So the solution -1 is repeated, if that makes sense. So it doesn't mean that you should have 4 or you shouldn't have n different zeros. It just means like that's the possible number. Okay. Next is the complex conjugates theorem. So if f is a polynomial function with real coefficients and a plus bi is an imaginary 0, then a minus bi is also a 0 of f. So if you're given that an imaginary or complex number is a 0, then the conjugate is also a 0. And the irrational conjugates theorem says the same thing but for radicals. So if we're given that a plus rad b is a 0, then a minus rad b, or the conjugate, is also a 0. Okay, so for example, here we want to find all zeros of the polynomial function. So we're going to list them all like we did in the last section. And since the leading coefficient is 1, this is not too bad. So we have 1, 2, 3, 4, 6, and 12. So I just listed out all of the factors of 12. And then let's use synthetic division to figure out which ones work. So I'm going to try -1. So that's going to be 1, 4, 7, 16, and 12. So that's 1, 3, 4, 12. Okay, so that means we know that -1 is a 0. And then we can do this again for another number. So let's do -3. And we get 0 again. So now at the end, 104 means x squared plus 4. So we can set it equal to 0 to find what it is. So for this, we can subtract 4 on both sides. So we get x squared equals -4, and then square root both sides. So we get x squared x equals plus minus 2i. Since the square root of 4 is 2 and the square root of -1 is I. So that means the zeros are, or are we solving this? Okay, well, either way, x equals -1, -3, and plus minus 2i. Okay, next one. Oh, and since there are 4 different zeros here, if we check our degree, it's 4, so we have 4 zeros. Okay, next one, we have 1 as our leading coefficient and -8 as our last numbers. That's 1, 2, 4, and 8. So let's try 1. And we get 0. And let's try -2. Okay, so both of those worked, and we get the same thing. So we get x squared plus 4 equals 0. So x squared equals -4, so that means x equals plus minus 2i. So the zeros are x equals 1, -2, and plus minus 2i. So you won't always get x squared plus 4. These two problems just happen to be that. But you can use the quadratic equation or square roots like we did for these to solve and figure out what imaginary or radical solutions we have.